Welcome students, welcome back to the series of lectures on matrices. In the previous lecture we introduced the concept of multiplication of matrices and we saw some of the properties. So, let us proceed further by doing some more properties on the multiplication of matrices. First one, matrix multiplication is associative. That is, for any three matrices A, B and C such that A and B are compatible for multiplying and B and C are compatible for multiplying then A dot B dot C is equal to A dot B dot C. So, let us prove this. So, let A be n by m matrix B be m by r matrix and C be r by s matrix. So, this is possible because because of the given hypothesis. So, this kind of choice for n and m, n, m, r and s, right. So, this is the hypothesis that we have, A and B are compatible for multiplying and similarly B and C are compatible for multiplying. So, what you have is that A is an n by m matrix, B is an m by r matrix and C is an r by s matrix. So, let A equal to Aij, right, 1 less than or equal to I less than or equal to n, 1 less than or equal to j less than or equal to m, B equal to Bij, 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to r, and finally C equal to Cij, 1 less than or equal to I less than or equal to r and 1 less than or equal to j less than or equal to s. Now, let us try to calculate A dot B dot C. A dot B dot C is A dot B is this matrix Bij dot with Cij, fine. Now, if you multiply these two, the resulting matrix will have the following thing, k running from 1 to r, b I k c k j. So, one should notice carefully over here, right, that these two are compatible, therefore, this makes sense, which is equal to Aij with this matrix whose entries are given by summation k running from 1 to r b I k c k j. right. Now, let us try to expand it out. Let us again multiply these two equal to the entry is going to be summation t running from 1 to m a I t. So, the remaining is going to have what you want is the maybe if I am going to call the product of B and C as the matrix D with entries d I j. So, what I needed is d t j, right. This is the I jth element I wanted. So, where d t j is the t jth entry in the matrix B dot C. So, this is going to be equal to summation t running from 1 to m a I t and d t j, let us write it down, summation k running from 1 to r b t k c k j. This is what I have, which is equal to summation t running from 1 to m summation k running from 1 to r a I t b t k c k j. This is what I have finally. After expanding all the brackets, I have this. So, the finally a dot b dot c, the I jth entry is given by this formula. Now, let us try to calculate the other one a dot b dot with c, which is going to be the product of matrices with entries a I j times the product of times the matrix with entries b I j times with c. So, this we know by product rule, the entries are given by summation k running from 1 to m a I k b k j a I k b k j. So, dot with c equal to, let me write down summation k running from 1 to m a I k b k j. These are the entries dot with c I j, which is going to be equal to the I jth element. So, I will have to multiply. Let me just use the same thing, summation over t running from 1 to r. I need the ith element. So, summation t running from 1 to r. So, the ith element is summation k running from 1 to m a I k b k t. This is the ith element, this whole thing multiplied with, I will have to multiply it with the t jth element of this, which is exactly the c t j. This is what I have, which is equal to summation t equal to 1 to r summation k equal to 1 to m a I k b k t c t j. Right now, what you will have to notice is the following. We will have to notice that this is same as what we had the expression for a dot b dot c. So, how to compare it? So, what we will do in this case is let us interchange the roles of t and k, or because they are just the dummy indices. So, I will just write it as replace t by k and k by t, k equal to 1 to r and t equal to 1 to m. I have replaced k by t, ait, and t by k, bkt, sorry, btk, yes, and ckj. This is what I have. Now, just look at the expression that we had last time, and you can notice that this is exactly same as a dot b dot c. Thus, we have shown that the matrix multiplication is associative. The next one natural question that one will ask is about commutativity. The truth is that matrix multiplication is non-commutative in general. So, in fact, let us do an example. Let us look at an example for this. Let a equal to 1, minus 2, 3, minus 4, 2, 5 and b equal to 2, 4, 2, 3, 5, 1. First, let us try to compute AB. AB equal to 1, minus 2, 3, minus 4, 2, 5 times this b 2, 3, 4, 5, 2, 1 equal to 1 into 2, 2, minus 2 into 4, minus 8, 3 into 2, 6, so plus 6, 1 into 3, minus 2 into 5, so minus 10, 3 into 1 plus 3, minus 4 into 2, minus 8, 2 into 4 plus 8, 5 into 2, 10 plus 10, minus 4 into 3, minus 12, 2 into 5 plus 7, 5 into plus 10 plus 5 into 1, which is 5. The resulting matrix is 2 minus 8 minus 6 plus 6, which is 0, 3 minus 10 minus 7 plus 3, which is minus 4, 8 minus 8 0 plus 10, which is 10, minus 12 plus 10, which is minus 2, plus 5, which is 3. On the other hand, let us try to compute BA. BA equal to 2, 3, 4, 5, 2, 1 times 1, minus 2, 3, minus 4, 2, 5 equal to 2 into 1, 2, 3 into minus 4, so minus 12, 2 into minus 2, which is minus 4, 3 into 2, 6, so plus 6, 2 into 3, which is 6, 5 into 3, 15, so plus 15, 4 into 1, 5 into minus 4, which is minus 20, 4 into minus 2, which is minus 8, 5 into 2, 10, 4 into 3, which is 12, 5 into 5, which is 25, so plus 25, 2 into 1, 2, 1 into minus 4, so minus 4, 2 into minus 2, which is minus 4, 1 into 2, which is 2, 2 into 3, which is 6, plus 5, 1 into 5, which is 5. The resulting matrix is 2 minus 12, which is minus 10, minus 4 plus 6 which is 2, 6 plus 15 which is 21, 4 minus 20 which is minus 16, minus 8 plus 10 which is 2, 12 plus 25 which is 37, 2 minus 4 which is minus 2, minus 4 plus 2 again minus 2, 6 plus 5 which is 11. You can notice the following, that AB is a matrix of order 2 by 2, while BA is a matrix of order 3 by 3, and also the entries of A and B cannot be matched. So, once you have that these two are of matrices of different order, these two cannot be compared, therefore, AB is not equal to BA. A natural question is, how about square matrices of same order? Let us look at another example. Let A equal to 1, 2, 3 and 4, and let us choose B as 5, 6, 7 and 8. Now, let us try to compute AB which is 1, 2, 3, 4 times 5, 6, 7 and 8, which is equal to 1 into 5, 5, 7 into 2, 14, so plus 14, 1 into 6, 6, 2 into 8 which is 16, 3 into 5, 15, 7 into 4, 28, 3 into 6 which is 18 plus 4 into 8 which is 32. The resulting matrix is 5 plus 14 which is 19, 6 plus 16 which is 22, 15 plus 28 which is 43, 18 plus 32 which is 50. Now, let us try to calculate BA equal to 5, 6, 7, 8 times 1, 2, 3 and 4, which is equal to 5 into 1 5 plus 6 into 3 which is 18, 5 into 2 10, 6 into 4 24, 7 into 1 7, 8 into 3 24, 7 into 2 14, 8 into 4 32, which is equal to 5 plus 18 which is 23, 10 plus 24 which is 34, 7 plus 24 which is 31, 14 plus 32 which is 46. Thus, AB which is equal to 19, 32, 43 and 50, and you can notice that not even a single entry is equal to the entries of the matrix BA 23, 34, 31 and 46, which is same as, right. Therefore, AB is not equal to BA even when A and B are square matrices of same order. The next property that matrices in general possesses is the following. So, for example, if alpha and beta are any two scalars such that alpha dot beta, when you multiply these two and if the resulting a 0 scalar, then either alpha equal to 0 or beta equal to 0, one of these happens, but this does not happen in the case of matrices. So, let us look at a simple example where this fails. So, let A equal to 0, -1, 0, 2 and B which is 3, 5, 0, 0, you have this. You have these two. Now, let us try to compute AB. 0, -1, 0, 2 with the matrix 3, 5, 0, 0, going to be 0 into 3 which is 0 plus -1 into 0 you will have 0, 0 into 5 you have 0, -1 into 0, so it is again 0, 0 into 3 it is 0 plus 2 into 0 which is again 0, 0 into 5 it is 0 plus 2 into 0 will have 0. So, the resulting matrix is just the 0 matrix. So, matrices, although they look like as if they behave like real numbers or complex numbers, they have their own set of properties, that is they are highly non-commutative, and similarly even if you have two non-zero matrices, their product can lead to this 0 matrix. Now, let us move on to the concept of what is known as or elementary row operations and row echelon matrices. Let us first begin with defining what is a row echelon matrix and then try to understand what is known as the row operations. Fine. So, let us begin with the definition. A matrix is called row reduced echelon, right, or a row echelon matrix if the following properties hold. First one, every 0 row is below every non-zero row. Second one, the leading coefficient what does it mean by a leading coefficient? First non-zero coefficient of every row is 1. Well, the third one, a column which contains a leading non-zero entry contains the leading, because the second one says that the leading coefficient should be 1. So, which contains the leading coefficient and 1 of a row, right. If you have a column which contains the leading coefficient 1 of a row, has all the other coefficients equal to 0. Right. So, you have 3. Now, the last condition, fourth one, suppose the matrix has r non-zero rows, that means that the remaining rows are 0, right. Matrix has r non-zero rows. If the leading non-zero entry of the ith row occurs in the kith column, then what can you say about K1, K2, Kr? Then K1 is strictly less than K2 up to strictly less than Kr. These are the 4 things that you need to define the notion of what is known as the row reduced echelon matrix. Now, let us do some examples. First one, let us look at this one 1 0 2 0 0 0 0 1 0. The first condition says that every 0 row is below every non-zero row. So, the second row is a 0 row, but it is above a non-zero row, right. The second row is above a non-zero row. The third row is non-zero, and because what we want is that every 0 row should be below every non-zero row, and the second row, which is a 0 row, is above a non-zero row, and hence not row reduced and not a row reduced echelon matrix. Let us look at another example. Second one, the same thing. So, let us swap the second and third rows 1 0 2 0 0 0 0 1 0. So, you have 0 here 1 0 1 1 2 0. Right. So, this is the matrix that you have 1 0 1 0 2 0 0 0 0. So, first one, the 0 row, here is the last one which is below all the non-zero other non-zero rows. Second one, the first leading coefficient should be in every row should be 1, which is the first non-zero. In the first row, this is the first one, first leading coefficient which is non-zero, this here. In the first row you have 1, which is fine, but in the second one you have 2. So, the first leading coefficient or the first non-zero coefficient in the second row is 2, and hence not a row reduced echelon matrix. Let us look at another example. Let us look at this one 1 1 2 0 1 1 0 0 0. The 0 row which is in the third one and it is below the other two 0 rows or the other two non-zero rows. The first leading coefficient in the first row is the first element which is 1, and similarly for the second row it is the second element which is again 1. But if you notice the third condition that you need for a row reduced echelon matrix is that if wherever you have the first leading coefficient, then the other entries of that column should be 0. So, if you have 1 over here, so the other entries are 0 here, but you have 1 which is the leading coefficient, but then you have 0 here, but this is non-zero, right. Hence, this is not a row reduced echelon matrix. Let us look at one more 0 1 2 1 0 3 0 0. You have this. So, the 0 row which is the third row which is below all the other rows, the second row. So, the first leading coefficient is here in the first row and the first leading coefficient is here in the second row, all these are 1, and wherever you have the leading coefficient the other entries in that column are 0. You have 1 in the first row second column and the other entries in that column are 0, and you have 1 in the first entry in the second row is 1, right, and the other entries are 0. So, K1, so you have two non-zero rows. So, what you wanted is the kith column, the fourth condition. K1 is 1 in this, sorry, 2 in this case, which is the second column, and K2 in this case is 1. Therefore, what you have is K2 is less than K1. Therefore, this is not row reduced. So, this matrix is not row reduced. Let us look at another example 1 0 2 0 1 3 0 0 0. So, you can notice that the 0 row the third row is below all the non-zero rows, first thing. Second, the leading coefficient or the first non-zero coefficient in both first and second row, leading coefficients in both first and second rows are just 1, right, it is just 1, and therefore, you are done. The third one that you wanted is that all the elements, right. So, the elements in a column containing a leading coefficient all the other elements, right, in a column containing a leading coefficient or 0. So, leading coefficient appears in first column and second column. You can notice that apart from this one, the remaining two elements are 0. Last one K1, right, the first one appears in the K1th column or first column, K1 is 1, K2 here it is second 2, so K2 is 2. So, therefore, K1 is less than K2. So, thus this matrix is a row reduced echelon matrix. Now, the natural question that one would like to ask at this stage is the following question: given a matrix A, is there any procedure to convert it into a row reduced echelon matrix? This is the question. So, let me repeat the question: given a matrix A, is there any procedure to convert it into a row reduced echelon matrix? Yes, there exists a procedure, and the procedure is to apply what are known as elementary operations or what are known as row elementary operations. So, let us first discuss what these row elementary operations are. There are 3 row elementary operations. First one, multiplying the ith row by a non-zero scalar. Say lambda. So, we will denote this by the ith row is replaced by lambda times Ri. Let us do a simple example. You look at this matrix 1, 2, 3, 4, 5, 6. You just multiply the first row by 2 times of it one. What will you end up with? You are multiplying the first row by 2. So, 2 into 1 it is 2, 2 into 2 it is 4, and 2 into 3 is 6. 4, 5, 6. This is what you have. So, the new matrix 2, 4, 6, 4, 5, 6 is obtained from the first one by just multiplying the first row by the scalar 2. Second one, interchanging ith row and jth row, right. This will denote it as the ith row and jth row are swapped or interchanged. This is the notation that we will have. So, let us look at one example: 0, 1, 2, 1, 0, 3, 0, 0, 0. So, this is an example. So, what is that we are going to do? We are just going to swap R1 and R2. And what will you have if you swap 1, 0, 3, 0, 1, 2, 0, 0, 0. The third row elementary operation, replace the ith row by the sum of ith row and a mu multiple of jth row. You are replacing the ith row by Ri, the ith row, plus a scalar times the jth row. So, we are replacing the ith row by Ri, the ith row, plus the scalar mu times the jth. This is what we have. So, let us do an example for this. The matrix that you have is 1 2 0 0 0 0 1 3. This is the matrix that we have. Now, let us do the following. R 1 is replaced by R 1 plus 2 times R 2. This is what we have. We are just multiplying 2 times R 2. So, first one is R 1 is 1, 1 plus 2 times 0 which is 1, 2 plus 2 times 0 you will end up with 2, 0 plus 2 times 1 you will end up with 2, 0 plus 2 times 3, so you will end up with 6. So, 0 0 1 3, this is the one that we have, right. So, these are the 3 elementary operations that we are going to perform to obtain what is known as the row echelon matrix. Now, what is the procedure that we will have to apply to get a row reduced echelon matrix from a given matrix? So, procedure to obtain a row reduced echelon matrix from a given matrix So, the following are the steps. So, let me just denote them by dots. First step, well, let me write it as step 1 because we may have to repeat certain steps again and again. First thing that you will have to notice is that every 0 row is below every non-zero row, that you will have to verify. So, if that is not the case, apply interchange of rows. To push down the 0 rows to the end of the matrix. So, once you do this, what will happen by the end of this? All the 0 rows will be below every non-zero row. Now, the second one, step 2, find the first non-zero column. You will have to find the first non-zero column. In fact, I should write it as from left, right. You will have to start from the left, right. So, let us suppose that the first non-zero column, that it is K 1, right. K 1 is the first non-zero column. Step 3, again apply interchange of rows to push up. So, earlier we pushed down, now we are pushing up. To push up a row whose leading non-zero coefficient occurs in first non-zero column. To the first row. So, I want this to be in the first row. If this coefficient is not 1, then what will I do? Divide the first row by the leading non-zero coefficient divide the first row by the leading non-zero coefficient, so that the leading non-zero coefficient becomes, I want that to be 1. Now, step 4, next apply the last elementary operation Ri replaced by Ri plus mu times Rj for suitable values of j and, in fact, I should write it as mu and R1, right, this should be R1 for suitable values of I and mu, so that the first non-zero column has non-zero coefficients only in the first row. Now, step 5, repeat steps 2 to 4 for the submatrix obtained by deleting the first row and first column until all the non-zero rows are exhausted, right. Until you finish all the non-zero rows, keep applying this again and again and again. So, now let us do a simple example 1 1 2 1 2 1 1 2 3. This is the matrix that I have. So, what are those things that we will have to do? First step, look if there are any 0 rows and then apply interchange of rows to push them to the last one. Now, if you look at this matrix, there are no 0 rows and hence you do not have to apply this first one. Second, identify the first non-zero column, which is the first column itself, and then make sure that look at the first non-zero coefficient in that column where it appears, the row in which it appears. Again it is in the first row, first column, so there is no problem. So, the next thing that you will have to do is make the, so it is again 1. So, we do not have to divide, you will have to do is look at the other entries, they are non-zero. So, how to make it 0? Replace R2 by R2 plus minus 1 times R1, right. R2 is replaced by R2 plus minus 1 times R1. So, the first row is kept as it is. Second row R2 plus minus 1 times R1. So, you will have 0 here, R2 which is 2 plus minus 1 which is 1, 1 plus minus 2 which is minus 1, and then the last one again you replace R3 by R3 plus minus 1 times R1, you will have 0. So, again you will have 1. So, you will have 3 minus 2 which is 1. Now, what you do? You look at this submatrix 1 minus 1 1 1, look at this submatrix and then do the same operations. You do not have any non-zero things, non-zero rows, and well you will have to look at the first non-zero column which is this, and the first non-zero coefficient is this one which is again 1. So, let us not bother. So, we will have to convert the other things. So, what I will do? Replace R1 by R1 minus minus 1 times R2. So, I will have 0 1 minus 1 as it is. I am just converting R1 1 minus minus 1 into 0 which is I will have 1 1 minus minus 1 1 minus 1 which is 0, 2 minus minus 1 into minus 1 which is 1. Oh, I will have to write it as plus, sorry, it should be plus, right. So, 2 plus 1 which is 3, yeah. Again here last one R3 is replaced by R3 plus minus 1 times R2, right. So, R3, so I want this to be 0. So, I will have 0 here. So, 1 minus 1 which is 0, 1 plus minus 1 into 1 which is 2. So, I will have, finally, this is the one that I am the submatrix which is a 1 by 1 matrix, right. So, this is the only non-zero coefficient, and what I have is I should make this into 1. So, replace the last one is R3 is replaced by 1 by 2 times R3. I have other things 1 0 3 0 1 minus 1 0 0 1. I will have to make the other two elements 0 which is minus 1 and 3. So, let me just convert them into zeros. So, what I will do is I will replace R1 by R1 plus minus 3 into R3. So, what will I end up with? I will have 1 0 0, and similarly I will replace R2 by R2 plus R3, just R2 plus R3. So, what will I end up with? I will just end up with 0 1 0 0. This is the thing that I have, right. Thus, the row reduced echelon matrix obtained after applying the procedure or the algorithm to the matrix 1 1 2 1 2 1 1 2 3 is just the identity matrix. And with this, let me stop this lecture. Thank you all.